this great brand new year. And to start us off in our seminar series, we have David Kubiznak from the Perimeter Institute, who will be telling us today about the black hole analog of Wonderboss, so on.
Well, thank you so much. And first of all, let me thank you for inviting me here. So my talk will be about thermodynamics of black holes, which are asymptotically antidecited. And so it won't be based on an ADS-CFT correspondence, but rather it will be finding analogies between different systems. So maybe you are puzzled by the name Reentrant phase transition. I didn't know what they are about a few months ago. So first, a formal definition. So a reentrant phase transition is a transition where a monotonic variation of one thermodynamic variable, for example, a temperature, so I keep rising the temperature, results in several phase transitions where the initial state and the final state are macroscopically similar. So an example is here. It's actually the first observation of reentrant phase transition in 1904. So imagine that you have a mixture of nicotine and water. So on the x-axis, you have how many percent of nicotine you have in that mixture. And on the y-axis, you have the temperature. So you see this bubble here. So outside of that bubble, you observe just a homogeneous phase. You cannot recognize what is nicotine and what is water. However, inside that bubble, these two separate, and you see really two different components of the mixture. So in the upper half, you have perhaps you have nicotine above the water, and here you have water above the nicotine. So what happens if I increase the temperature? So let's say I start here. I have completely homogeneous phase. Then I undergo phase transition, and suddenly nicotine, splits from the water, and I have a layer of nicotine and a layer of water. Then they swap, and here I undergo another phase transition, and they again become homogeneous. So this is what is called reentrant phase transition. So changing the temperature monotonously, I undergo several phase transitions, and at the beginning I have macroscopically the same thing as at the end. Okay, so here's the plan of my talk. So I will start with some very basic review of Waals fluid and associated critical phenomena. Then I will repeat that basic black holes behave as thermodynamic objects, and you can talk about thermodynamics of black holes. Then I will talk about a new feature which entered thermodynamics of black holes a few years ago, and that is if you have a black hole in asymptotically antidecited space, then you can reinterpret the cosmological constant as a thermodynamic pressure. And that allows you to define something which is like a volume of the black hole, which is a thermodynamically conjugate quantity. Pressure is volume, and you can talk about volume of black holes. And once you have pressure and volume, you can basically compare black hole systems to fluid systems. And I'll be doing that. So then I'll repeat the basic facts about antidecited space, and then concentrate on black holes in antidecited space. And the simplest one is the Schwarzschild-Radius black hole and the famous Hawking-Page transition. Then you can add a charge to it, and I'll try to convince you that once you do that, you get something like Wonderboss behavior. Or you can go to higher dimensions, and you can get more complicated phase transitions, which, however, remind you what you see in everyday thermodynamics of simple substances. So you'll see these reentrant phase transitions, you will see a triple point, and so on. So let me mention my friends. So I'll be talking, the thing I'll be talking about is based on collaboration with these people, Natasha Altamirano, Sharmila Gunasekaran, Rob Mann, and Elham Sherkat Kanat. And it is also related to some older works with Miriam Sejic, Brian Dolan, Gary Gibbons, David Custer, Chris Polk here, and Jenny Trushen. So whenever you have questions, please feel free to interrupt me. Okay, as a prelude, we start with the Wonderboss fluid. So here you can see the coat of arms of Wonderboss family. So Wonderboss received the Nobel Prize in 1910 for his contributions to thermodynamics, and in particular for designing his famous equation. So here's the Wonderboss equation, which you learn about in high school. So basically, you modify your ideal gas law by adding two parameters, A and B. So parameter A is, measures the attraction between the molecules of the fluid, and parameter B corresponds to the finite volume of these molecules. And it's a modification of the standard law PV equals to T, which is the ideal gas law. So now, if you draw the isotherms, you get the standard PV diagram, and you see that for high temperatures, it basically behaves like an ideal gas law. However, there is a critical temperature where you see an inflection point, and below that critical temperature, you see this wobbling here. So the critical point you get from that equation, and in terms of the parameters A and B, you can get critical temperature, volume, and pressure. And there is a nice dimensionless quantity, which is called universal critical ratio, and that comes to 3/8. So whereas different fluids can have different A's and B's, so this ratio is universal. So it's a universal prediction for any kind of fluid, independent of A and B. And remember 3/8, because you will see that for black holes as well. Okay, so now you can play with that equation. So basically you can integrate that equation to get the Gibbs free energy. So Gibbs free energy is defined here as a function of temperature and pressure. And in order to get, so I can integrate my equation of state to get that. And so what is characteristic about the behavior of Gibbs free energy is that you see this swallowtail behavior from the catastrophe theory. So these are the slices of P equal to constant. So Gibbs is a function of temperature and pressure. If I make a slice of constant pressure, I get slices like that. And so here's a critical pressure, and under critical pressure, you see this swallowtail behavior. So now there is a thermodynamic postulate that the system wants to minimize the Gibbs free energy. Basically, you are in a state which minimizes the Gibbs free energy. And that means that below the critical pressure, there will be a phase transition. So for example, if I'm increasing the temperature and I'm over here, then instead of going up and up and up like that, I'd rather go directly here. So there will be a first order phase transition at that point. So the Gibbs free energy is continuous, but its derivatives are not, and that's why I call this first order phase transition. Okay, and alternatively, you can see this directly from the PV diagram. So there is this famous Maxwell equal area construction, which basically says, well, I have this isotherm here, but this oscillatory part of that is actually unphysical. And instead of going up and down, I rather make a shortcut here. So I find such a pressure so that the area of this bomb is equal to the area of that volume. And that's why it is called equal area. So for a given temperature of this isotherm, I can find a pressure where I actually undergo the phase transition between liquid and then vapor. Okay? And so once I know that, once I know critical pressure, when that happens for that given temperature, I can draw a coexistence line of the two phases. So, which is exactly this thing here. So to this temperature and that pressure, I find a point on that coexistence line. So if I'm for small temperatures, I'm in the liquid phase. If I'm exactly there, I'm changing liquid to the gas. And if I'm above, I have gas. And this is the standard coexistence line of the first order phase transition. So now at the critical point, this becomes a second order phase transition, which will be characterized by critical exponents. So critical exponents basically describe the behavior of physical quantities near the critical point. They are believed to be universal, so there are various universality classes for various systems. But it may happen that completely different systems have the same critical exponents. So here is an example. So if I have a fluid with the critical point at Tc, Vc, and Pc, then, for example, I define coefficient critical exponent alpha to be is characterizing the behavior of a specific heat at a constant volume. So I calculate specific heat, and then this small t is T minus T critical over T critical. So it's the behavior at basically at critical temperature. And if I find that CD basically behaves like T to the power alpha, that defines the exponent alpha. And similarly, you can talk about the specific volume, how it behaves near the critical critical point, or the compressibility, or the pressure. So if you calculate these things for Wonderboss fluid, you get these critical exponents 0, 1/2, 1, and 3, which are basically they can be calculated using the mean field theory approximation. But you'll find the same critical exponent, for example, for other systems like ferromagnets and so on. Okay, questions? So now black holes. So let me briefly review black holes as thermodynamic objects. So I think Eddington once said, well, imagine that you created a new theory, and so this theory turns out to be inconsistent with quantum mechanics and special relativity. Well, who cares? They are wrong anyway. Well, it completely contradicts all the experiments. Well, these experimentalists, they don't know what they measure, right? But anyway, if it contradicts the laws of thermodynamics, then I give you no hope. So this is a famous quote from Eddington. So black holes, indeed, they behave like thermodynamic objects. The simplest black hole is the Schwarzschild black hole, and it's described by the spherical symmetric geometry. If you want, there is a horizon of the black hole located at 2m, at the radius equal to 2m. So the metric is static. That means, so basically using the Lateral theorem to any symmetry, I have a corresponding concept quantity. In particular, if my metric is static, I expect something like conserved energy. And so here's the prescription how to do it. So I have so-called Killing vector field, which is T, and there is a prescription how to calculate the corresponding conserved quantity, and that turns out to be the mass of the black hole, and that's conserved. So it's conserved energy. Another characteristic of the black hole is the surface gravity. So basically, I calculate a gravitational force on the horizon of the black hole. So here's the formal formula, but don't mind that. Just think about the classical Newton's law. We have Gm over r squared as the gravitational force. So now I take G equals to 1, of course. Now m over r squared, and I take r on the horizon of the black hole, where r equals to 2m. So I have m over 2m squared, which is 1 over 4m. So this is precisely comes out as in Newton's gravity, if you want. Then you can calculate the surface area of the horizon. It comes out to be 4 pi r squared. And it was known that actually proved by Hawking and others that this thing actually never decreases in classical processes. And so phenomenologically, you can take all these quantities. You can take the mass, you can take kappa, and you can take A, and you can play with them, and you will find out that actually they satisfy this so-called first law of black hole mechanics, dm equals kappa dA, which, however, Bekenstein said, well, maybe they are rather not a separate law, not an independent law, but they look like a first law of black hole thermodynamics. And indeed, on the left-hand side, you have something like an energy, right? So we just discussed that M must be an energy here. So this would actually be the same law if you can say, well, temperature is sort of proportional to kappa, and the entropy is proportional to the area of the black hole. And indeed, this was shown by Hawking 74 by calculation using quantum field theory in curved space-time, that indeed the temperature is related to the kappa, and the entropy is related to the area of the black hole. So I don't want to go into this, but there are many other derivations. So many other approaches to this problem. So one of them, I think the simplest one, is this Euclidean class integral approach, where you basically use the standard quantum field theory techniques to actually first calculate the partition function. From there, you calculate the free energy. And once you have the free energy, you calculate the entropy, and you independently prove that actually it is related to the area as A04. Also, because you know that the original manifold was non-singular at the horizon, if you actually continue this geometry into Euclidean thing, then it must be also non-singular, and that gives you that actually temperature is given by the formula there. There are many other approaches. I don't want to go into those. I think they all agree in these basic two equations, and they predict different corrections to these things. And I guess on these corrections they don't really agree. So, but they all basically agree on that. Okay. So now we can really talk about black hole thermodynamics, not black hole mechanics, but really we say all these things are actually the classical thermodynamics. So far I discussed just these two terms, but if you have angular momentum in your black hole, then you add the term like that, where omega I are angular velocities of the horizon. If you have charge, you can add, so this is an electric potential, and there's another term like that. You can also write down an integrated formula for these things. So basically I can consider the formula for a finite mass and finite entropy and so on, and that's called Gibbs-Stephen, Smart-Gibbs-Stephen relation. So this is all very nice, but in the standard law of black hole thermodynamics, we have PDV term, right? So what is the PDV term here? So you may sort of argue that all these things are work terms, and they are basically on the same footing as PDV, but they are not really PDV, right? They are other work terms. And I will try to convince you that this PDV term there, you can introduce once you have a cosmological constant, namely the negative cosmological constant. Okay, so here is the picture. So you can think about lambda as a thermodynamic pressure. And in fact, it has units of pressure. So usually people, when they consider cosmology, they treat lambda as pressure, but a kinematic pressure rather than a thermodynamic pressure. So you have to make this generalization from kinematic to thermodynamic pressure. So here is the Einstein equation, including lambda. So Einstein denoted that as biggest blunder in his life introducing lambda. It turns out that, well, it seems that we are living in a world which has actually positive lambda. However, I will concentrate on negative lambda. So that's departure from reality. Okay, so now here's the identification. So in this beautiful paper, it's been discussed that really you can associate lambda, and it's very natural to do. And there's a nice geometrical derivation why you should do so. That you should associate negative cosmological constant with a positive pressure, and here's the formula. And so once you know what the pressure is, you can calculate a thermodynamic conjugate quantity, and that will have dimensions of volume. So in particular, if I will calculate that for a black hole, I will call that a volume of the black hole. So that provides basically a way how to talk about the volume of the black hole. So here we go. So now here's the extended first law for black holes in asymptotically antidecipher. So about this term I have VDP term plus other terms, omega, j, and so on. So first remark, we have now VDP, so I can calculate this volume V as dm over dp, just from the thermodynamic considerations. So I can really talk about the volume of the black hole. So you probably noticed that, well, I wanted in the first law PDV, but here I'm giving you VDP rather. So there's actually a shift of concepts here a little bit. So when I talked about Schwarzschild, I was trying to convince you that M is an energy. However, if you have a cosmological constant, I will now try to convince you that M is an enthalpy. It's a different kind of energy. So what is an enthalpy? Enthalpy is an energy to create a system and put it into the environment. So this is precisely what we will be doing. We'll be creating the black hole and putting it in an environment of the cosmological constant. So it's not so unnatural to actually say, well, M is an enthalpy. Okay? So now I can calculate V from that relation dm over dp. And usually what happens is that you can take the limit p goes to 0. So you can also talk about volume of asymptotically flat black holes. So in particular for Schwarzschild, you get this amusing relation that V comes out with 4 farads pi horizon radius cube, right? So as if the Schwarzschild black hole were a ball of radius r plus in an Euclidean space. So actually, there's still no explanation for this amusing thing. So why it comes out to be this thing here. And I had some discussions with Gary Gibbs and Steve Carlin and so on. They think there must be a reason, fundamental reason why this comes out, but it's just an amusing property. Okay, so here's the volume. So more generally, you may study this volume for various black holes, and then has been done this in paper with Chris and Miriam and Gary. So basically, what we have done is that we calculated this volume we took many black hole solutions in various gravities, supergravities, and so on, and calculated from that relation the volume. So we got some expressions which of course vary widely, and there's no order in them. However, what you can do is that you can check something which is called isoparametric inequalities. So what is an isoparametric inequality? So consider just an Euclidean space and consider a domain in that Euclidean space. So that domain has some volume V and some area A. Okay, so now I can construct this quantity R, which is the ratio of the volume of the domain and the area of the domain. And I will find out that, and there is a geometric proof to that for any domain like that, this ratio will be always smaller or equal than 1. And it will be equal to 1 if and only if you have a round ball. Okay, so for any other domain, it will be smaller than 1. So now we said, okay, so if V really, which we calculated from this thermodynamic consideration, is to be interpreted as a volume, maybe it satisfies the same relation. What we found out is actually exactly the opposite for AES black holes. So we found out that once we calculate the thermodynamic volume, we take A to be the horizon area of the black hole, and calculate this quantity, it always turns out to be bigger or equal than 1. Okay, and equality is if, and if only if it has spherical symmetric black hole. So for Schwarzschild AES, you get equality. For anything else, for Kerr AES, you get bigger than 1. So that's why we call it reverse isoparametric inequality, because it's exactly opposite that happens in Euclidean case. So far there's no general proof to this inequality, but in all studied cases, even with non-spherical horizon topology, if you consider black ring, for example, in high dimensions, still actually this inequality holds. So, and then you can say, well, for this equality can be expressed well. For a black hole of a given thermodynamic volume, the entropy, which is related to this area, is maximized for Schwarzschild AES black hole, which is sort of natural. Yes?
Maybe I should know the answer to this, I can't remember. But how do you do it for the black ring? Because if it's not asymptotically flat, then you normally have to first have the lambda term and then turn it off, right?
Exactly. So I was a little bit cheating here. So there's an approximate solution constructed in the black hole approximation, which is valid for large, thin black rings, for which you can calculate all these thermodynamic quantities and calculate volume. So that statement is known only in this thin regime. It's a very good question. So in general, we don't know about black ring, but not in that special class of solutions, yes. So another thing which is actually nice about once you treat cosmology constant as pressure and you add the corresponding terms, then you have these SMAR formula and then you have the first law. And in general, they are inconsistent if you have cosmological constant. So for example, for Schwarzschild black hole, I'll find m equals to 2Ts. However, if I have Schwarzschild AES black hole, this won't be true anymore. So even if I consider the first law like dm equals to TDS, and don't consider that term in the first law, that's fine, but SMAR will be inconsistent. So now, SMAR and the first law are consistent if you consider that. So here's the argument. So you start from the Eyelash Theorem. It says I have a homogeneous function so that it satisfies this relation here, then this is true. Okay? So applying to Schwarzschild AES, I consider my the mass of the Schwarzschild AES black hole as a function of the area and the pressure. So now, basically, this homogeneity you can translate to the dimensional argument. So I'll be interested in the dimensions of the quantities. So now the pressure is the lambda, and that's 1 over r squared. So it has units 1 over length minus 2. The area is length 2, and the mass is length. Okay, so now I use that. So 1 from here, so 1 times m. Now 2 times a minus 2 times p dm over d lambda. Now I use the first law, so I know that dm over dA is kappa. If I put it here, I know that dm over dv, dm over dp, or d lambda is volume, so I put it here, and I get the first law and then the smart formula. So once you do that, these two relations are actually consistent, and everything works.
By the way, you're missing an 8 pi denominator on your kappa dAs.
Yeah.
I had previously.
Yeah, somewhere, yeah, maybe pi. So yeah.
Yeah.
That's also, yeah, thanks. But basically it's true.
Yeah.
Okay, so now we have, so this is what we've seen before, black hole thermodynamics and AES. So now I'm saying you can do that, so you can put VDP in AES, and then you get in general the term VP here. And these two are related and consistent. And this is really what you find for general class of black holes in AES. So without the term, you don't get the equality. And actually, people try to amend that. So for example, when they considered planar AES black holes, that they were finding that they cannot satisfy Smart relation. So they artificially put some I don't know, coefficients here. So they put 3 halves here instead of 1 and so on, which was phenomenologically found to be true for planar AES black hole, Schwarzschild AES black hole. But it wasn't true for charged AES black hole and so on. So they invented another one, another correction to the Smart formula, and so on. However, this is completely universal and valid. So yeah. Okay, so finally, if you have the volume, you can play this thermodynamic thing, and so I'll be studying rotating in charge AES black holes in a canonical ensemble, so I'll fix charge, I'll fix the angular momentum, and I will relate what I get to fluid thermodynamics. So I will really associate the volume of the black hole with the volume of the fluid, the pressure of the black cosmological pressure P is the pressure in the fluid, and so on. Temperature of the black hole is the temperature of the fluid. So then the corresponding potential will be the Gibbs free energy. I'll again try to minimize that, and that will give me the equilibrium state, which I'll get. I can also use a criterion for the thermodynamic stability, and that will be positivity of the specific heat. So I just calculate the specific heat for a given black hole, and if it's positive, it's locally thermodynamically stable. It's negative, it's unstable. And then you can, study phase diagrams in PT plane, calculate physical exponents, and so on. Okay, so if you want, you can think about anti-de Sitter as an hyperboloid in 5 dimensions. I'll put some black holes in it. Okay, so what is an anti-de Sitter space? Is maximally symmetric solution of vacuum Einstein equations with negative cosmological constant. So here is the corresponding metric. So what is quite interesting about that space is that it acts like a confining box. So here is the picture. So it's r equal to 0, r equal to infinity. So now let's say you send a massive particle all the way to infinity. However, due to the gravitational attraction, it actually comes back in a finite time. So whatever you send away, it comes back at you. So this is not true for massless particles, but for mass itself true. Moreover, you have to impose some boundary conditions on your space because this is not globally hyperbolic. So basically, if I'm here, anything can enter through the infinity. So I have to provide the boundary conditions in order to have predictability. Okay, so now what it means Okay, so if I have a box of gas, then the particles in that in that box they move completely randomly. But it may happen that if I wait sufficiently long time, all these particles actually come to one place, right? So if I wait 1,000 years, then to 123 years, then at some point it may happen that all these particles will come to one point. If that happens in gravity, you form a black hole. Okay, so once you have a confining box. So because of this reason, actually, people conjecture that ADS space must be unstable. And this was conjectured, I guess, long time ago, but put first by Lafermos and Anderson in 2006. And then there was this sort of paper proving that in 2011, which attracted a lot of attention. So what these people studied is that they studied a collapse of scalar fields, very symmetric collapse of scalar field in ADS space. And so what they found out is, so here is the magnitude of perturbation of how much scalar field I put in. And here is the radius of the black hole I formed. Yeah. So the scalar field actually collapses from infinity and forms a black hole. That's the case of this line here. So if I have lots of scalar field at the beginning, the magnitude is big, then actually the scalar field just goes down to the radius equal to 0 and forms a black hole of that corresponding radius. Okay. However, if I put a smaller perturbation of the scalar field, smaller amount of scalar field, what happens is that the scalar field collapses, goes through the origin, doesn't form a black hole, goes to the infinity. However, there it is reflected back, so collapses back and forms a black hole. Okay, so that corresponds to this line here. It's basically like one bounce from infinity and then forms a black hole. Okay, so here's the picture. So I either form a black hole at the first instance, which is this line here, or I form a black hole in the second instance, which is this line here, or I go, and form a black hole. 2 bounces, 3 bounces, 4 bounces, and so on. So in the end, no matter how small my initial perturbation of the scalar field is, I in the end form a black hole. Okay, and that's basically what you mean by instability. So no matter how small perturbation of ADS space I have, it is vulnerable to forming a black hole. Okay, so that was the result, which has nothing to do with me, but just to remind you the confining box property. So now, once you put a black hole into your ADS space-time, so for example, the Schwarzschild black hole, so you assume Schwarzschild black hole like that, this is the ADS correction. This was studied in '83 by Hawking and Page, and they found very interesting thing. So here's the corresponding Gibbs free energy, and here's the temperature of the black hole. So they found that there is a minimum temperature for fixed pressure. There's a minimum temperature, this one here. Below the temperature, there are no black holes possible at all. Above that temperature, you have 2 branches of black holes. Branches of small black holes and the branch of large black holes. So now these have negative specific heat, so they are thermodynamically unstable. These have positive specific heat. So it seems that actually these black holes are definitely preferable because they have lower Gibbs, they are thermodynamically stable, and so on. So you would prefer these black holes. So now you can do something a little bit more. You can say, well, I couple this to a bus of particles. So I actually really want a thermodynamic equilibrium. So for that, I have to add radiation into my space-time. So this radiation would precisely compensate how much is Hawking evaporated from the black hole. Okay, so if you calculate the amount of radiation you need, it's very, very tiny. So you need only a few quanta of radiation. For that reason, the Gibbs free energy of the radiation is approximately equal to 0. Okay. So now, if I use my thermodynamic argument, I treat this as a one system. So I treat radiation plus black hole as one system. So then, at this range of temperatures, I see that this is the only possibility of the Gibbs up to here. And then here, this is thermodynamically preferable to large black holes because they have bigger higher Gibbs free energy. Okay, so here I rather be radiation, however here I rather be large black hole. So at this point here, which is called Hawking page temperature, you see there is a first order phase transition between radiation phase and the large black hole phase.
Sorry, can I ask a stupid question? So, okay, I have this radiation inside ADS, and it's bouncing around. Now, by the previous transparency, will it not form
Okay.
black holes?
Okay, so what I talked about in the previous transparency was just pure ADS. There was no black hole whatsoever. So now people got really scared because of this ADS-CFT correspondence, right? Well, if ADS is unstable, what if everything what we are saying is unstable? But actually people prove that once you have a black hole inside your ADS, that is stable. So you can form a black hole if you have pure ADS, but if you already have black hole, the system is stable. You don't form any more other black holes. So yeah.
Basically because things just fall into it.
Yeah,
And
yeah, I think so. Yeah. Yeah. So that is stable. That's fine. Good question.
But sorry, so my stupidity persists. So, but if I'm in the regime where, according to this picture, it is not thermodynamically preferable for me to have a black hole, then
Okay.
don't I still have?
I see. I guess there are definitely people who know the answer. I don't know the answer, but all this is basically like a quantum process, if you will. However, what I talked about before was
It's a completely classical thing.
completely classical formation.
Okay.
So I guess I don't know.
Okay.
I don't know. But let's look at yeah.
Does the formation of a black hole, I mean, does it change if you have massive versus massless? Because you were saying before that the massless particles actually don't bounce back.
They don't bounce back, but people usually prescribe anyway boundary conditions so that they do bounce back.
Okay.
So you really need to prescribe some boundary conditions, and reasonable ones are that they do bounce back. Okay, so here is a. So now I can do this for. I can do this for different pressure. So this was for fixed pressure, for one fixed pressure. However, for another pressure, this line will be slightly different. It will be at a different place, and I'll get a slightly different T-Hawking page. So I can make a graph of that. So for various pressures, I always find the Hawking page temperature, and that will be actually the coexistence line of the phase transition between the radiation phase and the large black hole phase. And it looks like that. It goes all the way to infinity. And you may say, well, this looks like a solid liquid phase transition where the coexistence lines also goes to all the way to infinity. Right? So maybe. By the way, so this was also reinterpreted as transition dual CFT, which corresponds to confinement deconfinement of particle and plasma. Also, what you can play a game with Schwarzschildius black hole is that here's the formula for the temperature. So that's simply what it is in terms of radius and the cosmological constant. So now I say, well, the cosmological constant is the pressure, so I just reinterpret this L square as pressure, reshuffle the terms, so that I get a form of that. It's basically the Wonderboss equation, but written in a different form. So now if you calculate that for Schwarzschildius black hole, that is formula here, then you get that B equals to 0 automatically, and that A in this formula equals to 1 over 2 pi. Okay, so now you can consider, so what that K is, so you can put in general for various topologies of the horizon of your Schwarzschildius black hole, you can put K here. So if K is equal to 0, you have a planar black hole. If it's just spherical, you get 1 and so on, and minus 1 for hyperbolic. So in general, you get this K here. So remember, A is the parameter which measures the attraction between the molecules. So for Schwarzschildius, you get a universal prediction 1 over 2 pi, okay, which is attractive and very nice. For planar black hole, it's also interesting. You get K equal to 0, so A equals to 0, B equals to 0, so you get ideal gas law. So actually this is an ideal gas law. For hyperbolic, you get minus 1 over 2 pi, which is not attractive anymore. It's actually rather repulsive. Okay, anyway, so we get some first, we are getting close to Wonderboss equation, except that we have this B equals 0 here. But this is as much as you can do for Schwarzschild. So now, let me go and add charge. So there are these two famous papers by Rockmeyers and Chamberlain and Johnson and Roberto and Paran. And they considered charge ADS black holes. It was basically at the time of ADS-CFT correspondence. So here's the formula. You just calculate the temperature. It's given generalization of what you've seen, but now there's a charge, electrostatic potential, and so on. You have that first law of thermodynamics. And then they came with this amazing analogy. So they say, well, as I have the formula for the temperature, this one here, 1 over beta equals to that. Okay. So they say, well, let's write it like beta, so reverse that. And this is nothing else than just the formula for the temperature. And then they say, okay, so I can relay this equation of state for the black hole to an equation of state for the fluid by identifying the temperature of the fluid is the charge of the black hole, the pressure of the fluid is 1 over temperature of the black hole, and volume of the fluid is this R plus. And if you do that, you get basically, so on the right hand side you see Wonderboss, and on the left hand side you see charge ADS black hole. So you indeed see that if you draw lines of constant Q, lines of constant T, you get the similarity. And they actually went much further, so they calculated, so there is a critical point, and they calculated the critical exponents for the critical point and so on. And they constructed Landau's theory for that. So and then they show that everything you get matches basically exactly what you get for Wonderboss. However, I can see one problem with this. So this is very nice analogy, but for thermodynamics, this analogy is a little bit broken because in thermodynamics, what is very important is that you distinguish intensive quantities and extensive quantities. So extensive quantity is something which depends on how much of that I have. So for example, volume is an extensive quantity. However, temperature is an intensive quantity. If I have two black holes, they're still the same one. Two of the things, they're still the same temperature as one of them. So however, now here, you are actually relating an intensive temperature to an extensive charge. So this is something which should be rather forbidden in thermodynamics. Okay. So however, so we looked at that and we said, well, let's play the same game. This is the temperature, but now we are playing the game is the lambda and the pressure. So we rewrite that in terms of the pressure. So here's the formula. Now R plus is related to the volume. It's 4/3 pi r cubed. So this is the formula for that. And now here is the black hole, and here is the Wonderboss fluid, and we are comparing the same physical quantities, right? So here we are comparing. Well, here's R plus, but you can put it with volume as well, thermodynamic volume. Here is the pressure of the fluid, and this is what you get. So it looks similar. You can calculate where this inflection point happens, and you can calculate the associated critical things, and you calculate that 3/8 precisely as you did get in Wonderboss case. You can study the Gibbs free energy. This is, well, analogous, it's not precisely. So here's Wonderboss Gibbs free energy. Here's a charge ADS black hole, Gibbs free energy, but you get the same swallowtail behavior, and you get similar PT diagrams. So you get a critical point here. There will be a transition from small black hole to large black hole. So here, as I plot this thing here, I increase the radius of the black hole. So here are small black holes, and then I will go larger and larger and larger. So instead of going this way up there, I rather want to minimize that, so I go down here. So there's a phase transition from small black holes to large black holes here. Okay, so that's why I get the corresponding phase diagram. So I have small black hole, large black hole. There's a critical point. You can calculate the critical exponents for that critical point. They can come out here exactly on the Waals critical exponents. And this is actually quite robust because no matter, so this is charge ADS black hole, but you can try some nonlinear generalizations of that. So for example, consider Born cell theory, you get the same critical exponents. You can go to higher dimensions, you can consider rotating black holes, and still you get the same critical exponents. Okay, so this is Wonderboss behavior. So we're comparing liquid gas phase transition to small black hole, large black hole phase transition. Here. So now we enter on phase transitions. I already explained. But let's go to more complicated black holes, right? So let's go to higher dimensions. So here's the definition. So monotonic variation of one thermodynamic quantity results in two or more phase transitions, so that the initial state and the final state are macroscopically similar. So here's the picture which you already know. And first it was published and observed, well, maybe it was observed before, but first it was noticed in 1904 in the literature by Hudson, the existence of these phase transitions. And then it's very common feature in thermodynamics of multi-component systems. So if you have more than one component, you see these things. Basically, you have one phenomenon, another phenomenon, and these phenomena compete with each other. And that, so whichever wins, you have that phase transition. And so you have that in Gauss and ferroelectrics and so on. There's a nice review on these things here. So now in an ADS analog, so you have to go to 6 dimensions, care ADS black holes in 6 dimensions. So if you plot the Gibbs free energy, you get, so for big pressures, you get lines like that. So very, very boring. However, there's a critical point here, so that starts to be interesting. And then you have this interesting behavior there, so let me zoom on that. So zooming on this line, here, you get something like that. So the radius of the black hole increases like that. And remember that you always want to minimize the Gibbs free energy. So if I start with high temperature, I'd rather be on the branch which goes all the way down there. But I want to be a large black hole if I'm at high temperature. However, at certain temperature here, I will have a phase transition to that branch, which are rather small black holes, right? Because these are small. So there's a first order phase transition to small black holes. And then if I want to decrease temperature even further, well, this doesn't continue anymore. So I have to jump up there. Okay, and then I have, again, a large black hole. Okay, so we call it a zero-order phase transition. Actually, this phenomenon exists in superfluids and so on. So really, there's a jump in the global minimum of the Gibbs free energy, and that's a Gaudic phenomenon. Okay, so if you draw a phase diagram, what you get is so P and T. So here, so there's a critical point over there. This line is a first order coexistence line, first order phase transition, and there's a zero order phase transition. So let's say keeping P equal to fixed, P equal to constant, I want to be first intermediate black hole, then I increase the temperature, I want to be small black hole, and then I increase the temperature, I want to be then large black hole. So basically, so intermediate, if you want, you can think about it large as well. So that I have a transition large, small, large. That's why it's called transition. Okay, so now people doing ADS CFT, they scream at us that we have to vary lambda, right? And varying cosmological constant corresponds to varying m on the CFT side, and people don't like that. So, however, this phenomenon is completely independent of that. So I can copy this fixed lambda, so this is the same thing, but for fixed lambda, now I have to vary the angular momentum of the black hole. Okay, but you see that so there's a corresponding J-T diagram, so I fix T, I go here, I'm large black hole, it's very, very tiny region, I can modify that, but in the tiny region of angular momentum, I go from large to small to large again for fixed angular momentum. So I don't need variable lambda, or I don't need something like that. This phenomenon is there. So one thing which is really puzzling to us is, I mentioned that these Reentrant phase transitions, they occur for multi-component things. So, however, here you have just one black hole, one rotating black hole. What is the multi-componency of that? So what you think it is that, so we observe this only in d equals 6 and higher dimensions. And it is known that in d equals 6 and higher dimensions, you have a very special feature of black holes. And that is that basically you can rotate them arbitrarily fast. So in 4 dimensions, you know that the curved black hole cannot rotate arbitrarily fast. There is a maximum rotation I can rotate a black hole, and then it becomes a naked singularity. In 5 dimensions, it is similar. However, in 6 and higher, you can basically spin it arbitrarily fast, and still you have a black hole. But the behavior, thermodynamic behavior, and the other behavior of these black holes changes drastically as you spin it very, very fast. So if you start with a spherical black hole, and you spin it, basically it flattens and becomes like a pancake. Right? So it's very, very thin, very, 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 very extended. But basically resembles a black brain. And indeed, you can study thermodynamics and you can study other properties of these things. And there is a basic like black hole, black brain phase transition. So if you spin it not fast enough, it behaves like a black hole. If you spin it fast enough, it behaves like a black brain. And so maybe it's actually exactly the competing of these two phenomena. That if you so the black holes which actually participate in these Reentrant phase transitions are almost very, very fast spinning. So it's basically on the border between the black hole and black brain. Or maybe that's the multi-componency of that. Maybe.
Is this spinning on one axis only, or?
This is only one axis. 2 axis now. Okay, so now if you spin it in 2, you get even more interesting thing. You get actually 2 first-order phase transitions, and they even match at one point. So what you get is an analog of solid-liquid gas, basically. So here's the solid-liquid gas phase transition in PG diagram. So here's what you get for black holes. So you have small black holes here, intermediate black holes here, and large black holes here. So if I'm in this region of pressures, I have a transition from small to intermediate to large black holes. There are 2 first-order phase transitions. They meet in a triple point, as it is for solid-liquid gas. However, contrary to that diagram there, so if I have, so I can change gas to liquid without actually undergoing the phase transition. So I can go around this critical point and avoid doing the phase transition. This is impossible if you go from liquid to solid. You actually, there is no critical point for this line. It goes all the way to infinity. So if I'm changing liquid to solid, I have to undergo the phase transition. So here it is not true. I can go here and I can go there as well. So there's another critical point. So this is not infinite. Actually, it becomes almost infinite in the limit of the second rotation parameter goes to 0. But for any finite, it actually it is there. Okay, so this was just to amuse you. So if you go to higher dimensions, I guess, and consider more rotation parameters and so on, maybe you can get more complicated phase diagrams. So let me conclude. So thermodynamics is a governing principle, and black holes are not an exception. So recently, people have been playing with this idea of identifying the cosmological constant with the thermodynamic pressure, and that actually gives you a possibility to define the thermodynamic volume. So by the way, people actually played with the idea of defining volume before of the black holes. Usually, so there are various definitions of for the volume of black holes. We now call them geometric definition of the black hole of the volume, and they for non-rotating black holes they coincide. You get the same thing for spherical black holes. However, if in rotation, they may differ. But there are many other geometric definitions for the volume of black holes. But anyway, so once you have that, you can try to find analogues with everyday thermodynamics, just doing the standard thermodynamics with this volume and with that pressure. So we found. So basically, the Hawking phase transition is not something like solid-liquid gas phase transition. If you add charge, you get Wonderboss phase transition. If if you go to higher dimensions, you can get reentrant phase transitions, you can get triple points, and so on. You also get some other useful properties, such as isoparametric inequalities. So even if you don't believe in this volume pressure business, then there are some inequalities which come out from these considerations. And the question is, if they are correct, can they be used for something? So once you have inequalities, you can use them, usually to forbid some processes in black hole dynamics and so on. So maybe, these inequalities play a role in some estimates, or you can forbid some processes and so on. You get the consistency of the smart relation with the first law. People consider even compressibility. Once you have volume, you can compress your black hole. So people consider compressibility, people consider the speed of sound, and so on. So finally, this can be also extended to asymptotically distributed black holes. Doesn't work that well, but still, if you're interested, I can talk about it later. And the question is, as I said, people doing ADS-CFT, they scream at us because we are basically varying M. So is there any reasonable interpretation in ADS-CFT of these things? So fortunately, all these phenomena, they do exist even if you don't vary lambda. But I think the interpretation is nicer if you do vary lambda. The question is, can has ADS-CFT anything to say about this? Well, let me conclude here.
Thank you. So we have time for questions.
So in your equation, if for example D is too large, we could get rid of VT10, so large.
You mean, okay, so you mean this business of infinite dimensional black holes?
Yeah, so because this D is in the
Yeah.
denominator.
We haven't looked at that. It's possible because everything simplifies there, right, in the limits. You're right, so this is finite, that is finite. That is actually. Yeah. Another interesting limit is actually D equals 2.
Yeah.
We looked at that limit, and actually it works there nicely. So D equal to 2 is fine. But infinite dimensional, I don't know, it seems that we can maybe get rid of that. But yeah, it's an interesting question because now people playing this is infinite dimensional black holes. Yeah.
I have a kind of big question about your inequalities. So I know that people use such things to exactly as maybe as you said, sort of prove various estimates for existence of notions of local mass and energy and so on. But I think the ones that I've seen people play with is always with asymptotically flat situation. And I don't know, have you talked to such folks who might be interested in your result for the IES?
I haven't. It's a good idea. Have you, Chris?
What sort of people are we talking about?
Gosh, I can probably dig out some names out of here, but the various geometers that I remember from Max, like of the pals of Gerhard Huisken, this crowd. Yeah, I can dig out some names out of the rusty.
It might be, because if somebody could use
Disc.
that, it would be great, right? That would be great.
Anything else? All right, well, thank you again.
Well, thanks.